Flow measurement philosophy centered on accuracy, reliability, and application fit. Flow instrumentation must be selected based on measurable benefit, accuracy, turndown, lifecycle cost, and maintainability, balanced against application risk and process complexity. Inline flow meters are preferred where their performance advantages justify the initial investment, particularly in services requiring high resolution, minimal pressure drop, or wide dynamic range. Vortex flow meters are the default selection for general purpose applications, offering robust performance across a wide range of fluids, liquids, gases, and steam, provided operating conditions support adequate Reynolds number and velocity stability. Where vortex meters are not technically suitable, alternatives must be chosen based on specific measurement priorities. Ultrasonic flow meters for large line sizes, bidirectional flow, or custody transfer gas applications. Electromagnetic flow meters for conductive fluids, including corrosive, slurry, or dirty surfaces. Coriolis mass flow meters for high-accuracy mass flow in liquid or gas systems, including chemical injection or blending. Thermal dispersion flow meters for low-range gas applications with consistent composition. Differential pressure flow meters, e.g. orifice, venturi, as a robust fallback when inline meters are not viable or where legacy compatibility is required. Positive displacement and turbine meters should be reserved for fiscal metering, where regulatory frameworks demand them or where mechanical count-based measurement is mandated. Proper flow meter selection requires comprehensive process data, including minimum, normal, and maximum flow rates, temperature, pressure, density, and viscosity, fluid phase, cleanliness, and composition variability. Startup and abnormal operating scenarios, e.g. wet steam, flashing, multiphase. Pressure drop and turndown ratio must be considered early. No flow meter should be selected on nominal conditions alone. The device must operate accurately and stably at all credible low and high flow conditions, especially if part of a control loop or safety function. For custody transfer, Coriolis and ultrasonic flow meters are preferred in liquids and gases respectively, subject to authority approval and compliance with standards, e.g. AGA 9 for gas. Flow directionality matters. Most meters are unidirectional and may falsely report forward flow under backflow conditions. For reversing or pulsating systems, bidirectional capable meters, ultrasonic, Coriolis, must be specified. Finally, the measured output must reflect the true quantity of interest. Mass flow meters should be selected where density variations are significant or where mass balance is critical. Where volume flow is used but mass is reported, pressure and temperature compensation must be explicitly engineered to ensure measurement integrity. Flow measurement is not about installing a device. It's about guaranteeing usable, trusted data under all process realities. The choice of flow instrument must reflect the full operating envelope, not just steady-state expectations. Vortex flow meters as standardized solutions for clean, high turndown applications. Vortex flow meters offer a dependable, low-maintenance solution for measuring clean liquids, gases, and steam in medium to large pipelines. Their core advantage lies in their wide turndown ratio, minimal moving parts, and suitability across a broad range of standard industrial services. By leveraging the von Karman vortex shedding principle, they translate flow velocity into a measurable frequency output, linearly proportional to volumetric flow rate. Vortex meters are inherently unidirectional and velocity profile dependent and function best in fully developed single-phase flows. Their robustness and ease of integration make them the default choice where process conditions support their operating limits. Performance limits and sizing strategy. Vortex meters exhibit a natural cutoff point below which vortex shedding becomes unstable or indistinct from background noise. Therefore, meters must be sized to operate above the minimum Reynolds number, preferably like 40,000. Maximum expected flow should fall within 35 to 100% of meter capacity, avoiding oversizing. If 2 meter sizes are technically viable, the smaller size is preferred, as oversizing raises the cutoff threshold and compromises turndown. Proper sizing is essential. Oversized vortex meters tend to exhibit erratic low flow behavior, hunting in control loops, and may fail to detect flow altogether at startup or during minimum load conditions. For control applications operating near minimum flow, a flow rate estimator based on valve position may be required as backup, but only with principal approval. Service limitations and application screening. Vortex meters are not suitable for two-phase flows, wet gas, flashing liquids, foaming. Services with cavitation risk, especially in low-pressure liquid lines. Viscous, dirty, or erosive fluids that may disrupt the shedding pattern or damage the shedder bar. They should also be avoided immediately downstream of compressors or pulsating pumps, unless dampers are installed. Installation considerations. Vortex meters must be installed in accordance with vendor-specified straight-run lengths, typically upstream and downstream of the meter body. Flow conditioners may be necessary in space-constrained layouts. To reduce buildup or fouling, shedder bars should be mounted horizontally in horizontal pipe runs. For gas services, the meter should not sit at the lowest point where condensate may accumulate. For liquid services, avoid high points where gas pockets may form. Downstream pressure must remain above the cavitation threshold under all operating modes. Where condensable gases may form slugs on restart, drain facilities must be included to protect the meter. Sensor technology and maintenance features. Non-wetted sensors are preferred for reliability and ease of replacement. For high-integrity services, dual sensors allow for redundant output, e.g., for parallel control and safeguarding functions. Vortex meters with removable electronics should be specified where high-temperature operation or difficult access is anticipated. Conclusion. Vortex meters are best in class for clean, steady, unidirectional flows where high turndown and low maintenance are essential. When properly sized and installed, they deliver long-term stability and measurement confidence. However, success hinges on careful application screening, flow profile control, and an adherence to installation best practices, making them a standardized solution, not a universal one. Ultrasonic flow meters for high accuracy, non-intrusive measurement in large and clean flow systems. Ultrasonic flow meters provide a non-intrusive, high-accuracy solution for measuring volumetric flow in large-diameter pipelines carrying clean liquids, gases, or steam. Operating on the transit time, time-of-flight principle, they measure the difference in signal propagation time between upstream and downstream directions, converting this into a precise velocity and flow rate. Only transit-time ultrasonic flow meters are acceptable. Doppler-based types lack the required accuracy and must not be used. Ultrasonic meters are profile-dependent, but do not obstruct flow, introduce pressure drop, or include moving parts. They are particularly advantageous in custody transfer, where accuracy and verification are critical. Large line sizes, where insertion of intrusive elements is impractical. Bidirectional service, where flow reversal must be accurately tracked. Low-pressure applications, where head loss must be minimized. Sensor configuration and application variance. Ultrasonic meters may use single-path, dual-path, or multi-path sensor configurations. The more paths employed, the better the compensation for flow profile distortion and swirl. For custody transfer or low Reynolds number services, e.g., flare lines, vent systems, multipath ultrasonic meters should be specified to ensure profile integration and accuracy. Some meters also offer an additional velocity of sound output, useful for gas composition tracking, e.g., molecular weight or fuel quality estimation, density estimation in clean, single-phase streams, mass flow calculation in flare or fuel systems with known fluid properties, clamp-on and insertion variants. Clamp-on ultrasonic meters offer non-invasive installation for liquids only, ideal for temporary measurement, retrofits, or delicate piping systems, e.g. glass-lined or non-metallic. Insertion probes may be used in permanent gas or steam installations, but must be equipped with retraction mechanisms for online maintenance, especially in critical or hazardous applications. Performance dependencies and limitations. While ultrasonic meters excel in many areas, they require clean, bubble-free fluids for reliable transit time detection, stable velocity profiles, especially in single or dual-path designs, protection from vibration, aeration, and noise sources such as cavitating pumps or low-noise control valves. Any significant gas entrainment or solid content can disrupt signal clarity. High-frequency noise from adjacent equipment may require the use of acoustic dampers or silencers, particularly when meters share lines with specialized low-noise valves. Installation standards and constraints. Sensor nozzles or clamp-on positions must be located in straight pipe runs per vendor guidelines. Nozzle alignment is critical. Misaligned probes compromise accuracy. For retrofits, in-field verification of pipe condition, e.g. scaling or lining, is necessary. In horizontal lines, nozzles should lie in the horizontal plane to prevent debris or bubbles from collecting around the transducers. Clamp-on sensors must be mechanically secured and protected from drift or vibration. Surface preparation and sonic coupling compound selection are critical to avoid attenuation of the signal, especially at elevated process temperatures. Integration and diagnostics. For systems not using intelligent transmitters, the velocity of sound output should be made available to the DCS or local diagnostic panel. This provides real-time insight into process health and fluid properties. Ultrasonic meters are particularly well-suited to fuel gas lines, flare metering, pipeline balancing, and large loop custody transfer, where accuracy, low maintenance, and minimal pressure impact are essential. Conclusion. Ultrasonic flow meters combine high accuracy, non-intrusive design with broad application flexibility, but only when installed and maintained to exacting standards. Their success depends on fluid cleanliness, sensor alignment, and profile control, making them ideal for engineered flow loops where performance assurance outweighs the complexity of deployment. Electromagnetic flow meters for conductive liquid measurement in challenging industrial services. Electromagnetic mag flow meters are the instrument of choice for conductive liquid services, offering obstruction-free, pressure loss-free, and highly accurate flow measurement. Operating on Faraday's law, they induce a voltage proportional to fluid velocity across electrodes embedded in a non-conductive liner. This makes them ideal for dirty, corrosive, abrasive, or multiphase-prone liquids, services where mechanical meters fail or degrade quickly. Mag meters are volume flow devices, inherently bidirectional and velocity profile dependent, yet relatively tolerant of mild flow disturbances due to their large electrode sensing area. They are widely applied across water treatment, slurries, chemicals, mining, and pulp industries. Service suitability and conductivity requirements. Mag meters require the process fluid to have sufficient electrical conductivity, typically above like 0.05 to 20 mA/s per centimeters, depending on electrode and signal processing technology. As a rule, water-based, ionic, and polar liquids are suitable. Hydrocarbons and nonpolar fluids are not measurable and must be excluded. Vendors must confirm minimum conductivity thresholds, particularly for ultra-pure water, alcohols, and solvents. Liner and electrode material selection is critical. The flow tube's non-conductive liner and wetted electrodes are the primary process interfaces and must be matched to fluid chemistry, pressure, and temperature. PTFE, chemically resistant but unsuitable for vacuum due to detachment risk. PFA, improved vacuum stability when reinforced, but not as form retaining at high pressure. Ceramic, high abrasion and corrosion resistance, but fragile and sensitive to thermal shock. Rubber neoprene, economical and suitable for water and sewage, but limited chemically. Capacitive coupled electrodes, embedded in the liner, are preferred in fouling-prone services as they are more resistant to coating or gas bubble-induced signal loss. Installation considerations to ensure full pipe and stable flow. The pipe must be completely full at all times to avoid signal noise from air pockets. Electrodes should be horizontal in horizontal lines to avoid coating or gas blinding. For vertical lines, flow should be upward to avoid empty pipe conditions at low flow. The flow tube must not be installed at high points in liquid piping or at low points in gas service. Mag meters are sensitive to upstream and downstream disturbances, so required straight lengths must be enforced. Where space is constrained, flow conditioners may be considered. Proper grounding and electrical isolation is mandatory. Signal integrity depends on a stable reference to fluid ground. Improper grounding introduces noise and drift. Grounding rings or electrodes must be connected directly to process ground, isolated from structural current paths, e.g., grounding through piping supports is not acceptable. verified per manufacturer instructions, especially in plastic-lined or coated piping. Protection against mechanical and process abuse. The inlet liner is vulnerable to erosion in abrasive or high-velocity surfaces. Inlet protectors or edge-hardened grounding rings may be required. Gasket selection is crucial. PTFE envelope gaskets are standard. Graphite gaskets are prohibited due to potential liner shorting. Spiral wound gaskets must not be used, as misalignment or edge intrusion can damage liners or affect measurement accuracy. Maintenance and application considerations. Mag meters are virtually maintenance-free, but in abrasive or fouling surfaces, routine inspection of liners and grounding rings may be warranted. Many vendors offer diagnostics, e.g., empty pipe detection, electrode coating alarms, which should be integrated into the DCS where supported. Mag meters are not suitable for steam, gases, hydrocarbons, or low conductivity solvents. In multiphase flows with entrained gases, they may overread or become unstable, especially at low velocities or with uneven bubble distribution. Conclusion. Electromagnetic flow meters are highly reliable and accurate in conductive liquid applications where other technologies struggle. Their success depends on proper fluid qualification, material selection, installation discipline, and electrical grounding. When deployed correctly, they deliver long-term stability in the harshest process environments with zero moving parts and no pressure loss penalty. Coriolis mass flow meters for direct, high-precision mass and density measurement. Coriolis flow meters provide true mass flow measurement, directly responding to the inertia of the fluid, independent of phase, density, or viscosity. Based on the Coriolis effect, they measure the twisting of vibrating tubes caused by fluid acceleration, yielding highly accurate mass flow, density, and in some models, temperature. These meters are ideal for custody transfer, blending, chemical injection, and high-value or critical services where volumetric assumptions are insufficient. Coriolis meters are profile-independent, bidirectional, and unaffected by flow disturbances, making them highly reliable even in short pipe runs or space-constrained installations. They are suitable for both liquid and gas flows, but not for steam. Unmatched accuracy for mass and multivariable outputs. Coriolis meters offer mass flow accuracy typically better than Pli's 0.1%. Density accuracy up to 0.0001 gram per centimeter cubed, enabling precise concentration and interface detection. Temperature measurement from the vibrating element for thermal compensation or monitoring. Many models also provide derived values such as volume flow, net mass for batch applications, concentration or bricks for multi-component streams, application screening and suitability. Coriolis meters are ideal for custody transfer of liquids and gases pending authority approval, blending, dosing, or filling systems requiring tight mass ratios, chemical injection, where small flow rates and variable viscosities make other technologies unreliable, non-Newtonian or viscous fluids, where viscosity or velocity profile distorts other flow measurement methods. They are not suitable for steam or multiphase flow, e.g. gas in liquids or flashing conditions, which cause signal instability. Slurries with high solids content unless certified by the vendor. Services with extreme external vibration or pipe strain without adequate isolation. Material selection must match process risk. Coriolis tubes are available in 316L stainless steel for general service, Hastelloy C22, C276, Inconel, Monel, titanium, or tantalum for corrosive, halogenated, or high-pressure services. For services containing chlorine or trace acids, stainless steel may suffer from stress corrosion due to vibration. Hastelloy or superior alloys must be specified, and vendors must validate fatigue resistance at the expected vibration frequency. Process constraints. Pressure drop and cavitation. Although Coriolis meters have no moving parts, they may introduce moderate pressure drop due to small bore or multi-tube geometries. Their internal volume must be kept full under all conditions. In liquid systems, ensure no cavitation or flashing under low pressure. In gas systems, confirm sufficient density and flow energy to sustain signal stability. Avoiding cavitation is critical. Vapor bubbles distort the signal and can permanently damage tubes. Installation best practices. Coriolis meters are compact but require stress-free mounting with independent pipe supports. Avoidance of pipe strain, use of flexible joints or bellows may be needed in tight systems or skids. Downstream shutoff valves to allow zero-point calibration under zero flow conditions. Preferably horizontal orientation with upward flow to maintain full tube condition, especially in low flow or draining services. No straight length requirement. One of the key advantages of Coriolis meters is that they do not require upstream or downstream straight runs, simplifying layout in congested installations or compact skids. Gas applications and limitations. In gas services, special attention is required. Lower gas density results in weaker tube deformation, reducing signal strength. Vendor-specific minimum density thresholds must be respected. Signal noise increases with pulsating flow or compressibility effects. Coriolis meters can be used for natural gas, hydrogen, CO2, and flare monitoring, but must be carefully sized and validated. Environmental and safety considerations. In humid or corrosive atmospheres, fully sealed hermetic electronics housings should be specified. Instrumentation for hazardous areas must carry appropriate X certification, XD, XIA, etc., and be suitable for the ambient environment. Conclusion. Coriolis meters provide unparalleled accuracy and versatility across the most demanding flow applications: mass, density, concentration, and energy-critical processes. Their high value is justified when measurement certainty, product accountability, or tight control margins are paramount. Successful deployment depends on correct material selection, stress-free installation, and process condition awareness, ensuring unmatched long-term performance with minimal intervention.